Okay, let's delve deeper into this concept of normal force. Um, Before we take a case where we will imagine a young boy moving in the, or let's say traveling in the lift, let us focus on something. How do we feel our weight, right? How do we feel our weight? We don't feel our weight because of the force that is acting on us, that is gravitational force. It's not because of that we feel our weight. Just reflect on this. We feel our weight because of the reaction to that weight. M into G is the weight, our mass into G is the weight that is acting on the ground, and I'm standing on the ground is giving a reaction. So because I am stationary, right? So there is no net force. That means the downward force, which is weight, has to be balanced by upward normal force. This normal force is sensed by my feet, right? So this sensory perception gives me feel of my weight, right? So let's understand this. Anyway, so consider 4 cases, and we have a person, a young boy of 10 kg, mass 10 kg. I'm taking mass 10 kg. So obviously the lift is closer to the ground, in the sense we are on near Earth's surface. So G is 9.8. That means the weight that will be acting downward is 9.8 into 10 in all the cases, right? Okay. So here we consider a case where lift is stationary. The way we will proceed is this. When we get into the lift, when the lift is stationary, then the lift starts, so lift accelerates. Then when we are near the floor to which we want to reach, or at which we want to get down, the lift will decelerate and then it will stop. Okay, so we start with the lift being stationary. So this boy is of 10 kg is in the lift. The lift is stationary, right? That means its velocity is 0, right? Velocity is a vector quantity, so I give a line here. So velocity is 0. Okay, so what is the normal force? It's obvious that the downward force is m into g, right? So the downward force is m into g, that is 98 Newton. I'm considering g is equal to 9.8 meters per second square. So 10 into 9.8 is 98 newtons downward. And since it is stationary, right, that means this force has to be balanced, right? Otherwise the person would just pierce through the lift. That's not happening. So it means that this floor is exerting upward force, which has to be exactly equal to this. So the normal force Fn is equal to 98 newtons, right? Okay. Let's go to next case. In this case, let's assume that this lift is accelerating, okay, and let's say it's accelerating at the rate of let's say 2 meters per second square, at the rate of 2 meters per second square, and we will consider, that means velocity is increasing in which direction? In vertical direction, right? So and increasing in the while it is moving above, right? That means upward. It's right, upward. So upward means it's positive, right? And vertical direction, up or down, that's vertical direction. I'll represent it by unit vector j, right? Or I could just show the arrow, but unit vector j, that means it's vertical movement we are considering. And acceleration, so this lift is now accelerating at the rate of 2 meters per second square. Now what will be the normal force, right? What will be the normal force? Now see, the downward force is going to remain same because we are closer to Earth. So this is going to be 98 newtons, m into g, right? This is m into g, 98 newtons. Now upward force, right, cannot be just 98 newton. Why? Because it is accelerating in upward direction. That means there is some net force in upward direction. If there is normal force only 98, then there will be no net force in upward direction. So what is net force in upward direction? Net force, Newton's second law, is equal to mass into acceleration. Sigma f, or f net, is equal to mass into acceleration. So mass is 10, acceleration is 2, so 20, right? 20 newtons is the net upward force, because the acceleration is in upward direction, net upward force. That means the upward force has to cancel out this 98 newtons, plus it should add 20 newtons net. That means the upward force, I'll write here the I should, instead of this let me make it here, Fn, right? Fn, so this is, I'll write here A is equal to 2 meters per second square in J direction. This is positive, okay? So Fn has to be 98 plus mass into acceleration. Mass is 10, acceleration is 2, so 10 into 2, right? So this is 98 plus 20, right? 98 plus 20, that is 118 newtons. So upward force is going to be 118 newton. The weight of the person is 98, but the reaction which he would sense is of 118. So he would feel heavier, and that's for our experience. When the lift is accelerating, we feel momentarily, when it is accelerating, we feel heavier than what we are. Okay, let's come to this. Now let's assume that we are near this, this person is near the floor at which he wants to get down, he or she wants to get down, and let's say now the lift is decelerating. That means in upward direction its velocity is decreasing, right? So acceleration is now minus, let's say minus, and we'll choose again minus 2 meters per second square, right? Minus 2 meters per second square. So now this is accelerating, and when it is accelerating, decelerating, negative acceleration. Now what will be the normal reaction? The normal reaction, now just think about it. Again, this is, the weight is going to be acting downward, right? Net force is mass into acceleration. It is again 10 into 2, 20, and it has to be in downward direction, right? It has to be in downward direction. That means what? If this is net force is to be in downward direction, the 98 is also in downward direction. That means there has to be upward force, which would, this is 98, right? 98, and the upward force, normal force, has to be equal to 78, right? Think about it, 78. So that net downward force is going to be 20 newtons, and net downward force is what? Second law of Newton, mass into acceleration. So net downward is 20, downward because of weight is 98, so upward has to be 78, so now downward will be 20. So this person will feel lighter because his weight is 98, but what he is sensing, the normal reaction is what he senses, and that is going to be 78, so he will feel lighter. Okay, let's consider this case where velocity is constant. Let's say it is moving at some 2 meters per second. Let's say, I'm just taking one figure. Its velocity is constant. Suppose the lift in between this and this, I should have considered this case here. Anyway, when the lift is traveling at constant velocity, what will be the normal force? Look, when the lift is traveling at with constant velocity, the net force is going to be 0. When net force is going to be 0, the downward force, of course, is weight, which is 98 Newton. So upward force has to be equal to 98, right? Upward force has to be equal to 98. So the person will not feel heavier or lighter. He will feel what he is feeling when the lift is stationary. So when the lift is stationary, when the lift is moving at constant velocity, that means acceleration is 0, net force is 0. So downward force, upward force have to balance. Remember, so that's why you know now why we feel sometimes lighter or heavier in the lift. Remember, in all these cases, simple equation is F net is equal to m into a. And what is F net? F net, when you write, it is the weight which is acting downward, that is mg plus Fn, right, is equal to m into a. Okay, now this is the equation. right? Why minus mg? Because weight is acting downward. You find out the value of Fn by transferring it here. What will change is A. When velocity is constant, A is 0. When velocity is 0, A is 0, right? And then that's it. When it is accelerating, right? Accelerating, then A is positive. When decelerating, A is negative. Substitute the values and you will get all these answers. Thank you.